Well, welcome back. In this segment, we're going to be studying the distribution known as the chi-square distribution. And we continue with the chi-square distribution with hypothesis testing, which you've just been mastering in chapters 9 and chapter 10. Well, the chi-square distribution is a distribution which is made up of squared values. And so the distribution will always be non-negative, meaning if you square zeros, it's actually made up of squared normals values. And so if you square 0, you'll get 0. But then you have negative and positive numbers that are squared, and you end up with a distribution that is only on the first quadrant, for example, if you were going to do a coordinate system. The chi-square distribution is also one of the most commonly used distributions. The notation that we have for this is a curved x with a square above it, and then we put the degrees of freedom in the subscript. The degrees of freedom for the chi-square distribution is the same as the mean, and the variance is equal to 2 times the degrees of freedom. The notation for the chi-square distribution is pretty simple, but the formula for actually figuring it out is very, very complicated. And we need to use a type of calculus involving numerical approximation to actually figure out the values. And so throughout the years of studying the chi-square distribution, textbooks have included charts that have values in it. Now we're fortunate enough that we can use technology, either computer software programs or graphing calculators that have the technology built in so that you don't need to use the tables in the back of the textbook. There are 3 main applications that we have of the chi-square distribution. The 3 main applications are the goodness of fit test, the test for independence, and the test of a single variance. The degrees of freedom are calculated differently for all 3 types of tests. And what I'm going to do is I'm going to discuss in this segment the goodness of fit test and the test for independence in detail. So in non-detail, and just now I'm just going to explain to you what the test of a single variance is. The hypothesis test for single variance is to see if the variance or standard deviation is within some value, some prescribed value, or if it is larger. This is used, for example, in quality assurance if we want to find out if the spread for a manufacturing piece of equipment is small enough, or is it so large that we need to calibrate the machinery. So for example, let's say you were going to buy a big jar of jelly beans, and you saw your jar of jelly beans and the jar's all next to it, and they had different levels in them, even though they had the same labeling and the same weight on the labeling. Well, you would certainly buy the largest one, but also you would notice that it's not consistent. And the machinery then that was calibrating the amount of jelly beans that go into each jar would have to be recalibrated so that we would have a more consistent. Now, we could keep calibrating and calibrating and calibrating until the consistency was exactly, every jar had exactly the same number of jelly beans. But what we might find out is that's so expensive to do that it's not worth the cost, that a little bit of spread or deviation is acceptable. And so the chi-square test of a single variance tests to see whether the spread by sampling, so we might sample 20 or 30, 100 jars of the jelly beans, count the number of jelly beans, and see if the spread is small enough that it's within an acceptable limit. If not, we go and calibrate the machinery. The 2 tests that we are going to do are the goodness of fit test and the test for independence. The goodness of fit test, the first one, what we're testing is to see if data follows a certain distribution. And so our null hypothesis for this one is going to be that the data follows whatever distribution we're testing. So the null hypothesis we have is the data does follow the distribution. Now, we need to customize this depending upon what it is that we're studying. The alternate will be that the data does not follow the distribution, and we'll need to customize that also. Our test statistic is the observed value, meaning the frequency, minus the expected value. We take that difference and we square it, divide by the expected, and then we add them all up. And we'll do this by hand and by calculator. And this will be our test statistic. At this point, we compare it and find the area in the tail to see, do we think that this is acceptable or not? We continue on. Once we find the test statistic, we continue on the same way we did in the previous chapters. If the p-value is less than alpha, we reject the null hypothesis. If the p-value is greater than alpha, we do not reject the null hypothesis. So it's the same concept. All that's different is how to calculate the test statistic. Let's look at this case right here. I have a die right up here. Here's the die. And what I'm going to be interested in is this die fair? Do we have a fair die or not? By seeing if the die is fair, I want to see, does this follow the uniform distribution for the discrete case? I should add that part. Or the data does not follow the uniform distribution for the discrete case. So what I did was I rolled this die 30 times. I rolled the die 30 times, and what I expected is if the die were fair, I would expect to get about 5 1s, 5 2s, 5 3s, 5 4s, 5 5s, 5 6s, if this were a fair die. If it's not a fair die, then I would expect a lot of variation. Well, I did roll the die, and I recorded what I got. And this is what I have right here. The face that showed up, a 1, showed up 7 times. A 2 showed up 4, 3, 5, and so on. I expected 5 of each. For the test for goodness of fit, the degrees of freedom equals the number of cells that the data could fall into minus 1. So in this case, we have 6 cells that the data could fall into. It could fall into 1, 2, 3, 4, 5, 6. So the degrees of freedom are equal to 6 minus 1, or 5. Now we need to calculate the test statistic. And so we'll do this by doing, the observed was 7. We expected 5. We square that difference, divide by 5, and let's see, 7 minus 5 is 2. 2 squared is 4, so we get 4/5. Now we go on to the next one. 4 minus 5 is 1 squared, divided by 5, and we get 1/5. 5 minus 5 is 0. 3 minus 5 is 2. 2 squared is 4, and we have 4/5 again. Notice that 7 is just as far off as 3. We expected 5, so we're 2 and 2 here. And this time we had 7 minus 5 is 2, which is positive. Here we had 3 minus 5, which was negative 2. And then when we square it, we get chi-square. We still have a positive right here, 0 and 1/5. We get our test statistic by adding these up. 4/5 plus 1 is 5/5. 5/5 plus 5/5 again are 10/5, or 2. Now, when we go to graph this, we're going to go to graph this. And the next thing we want to do is we want to have our graph. The chi-square graph, and you should try this with several graphs on a calculator or software program, changes shape depending upon the degrees of freedom that we have. The more degrees of freedom, the higher the number of degrees of freedom, the more the chi-square will start to look like a standard normal. So you can put right here, as n increases, the shape of the chi-square starts to look more like the shape of the normal. But notice that it will still be skewed. Notice that it will still have a heavier tail on the right side, and so it will still be skewed to the right. There's more, so it will go on, and it will still come down, but it will always be a little bit skewed to the right. Okay, now when we go to graph this, the degrees of freedom is just past the peak. This is where the average is. The lowest value is 0. And we have a right-tailed test. Our test statistic is 2. Well, here's 0, here's 5. So I'm not sure where 2 is, maybe right around here. And we're going to shade in the right-tailed. Now, the reason it's only a right-tailed test is if all of these happen to be 5s, 5 minus 5 is 0, 5 minus 5 is 0, and so on, we would have a test statistic of 0. So what that would tell us if we had a test statistic of 0 was that our observed was a perfect fit for the expected. Well, if we got a perfect fit, we're not going to reject that it's a good fit. We would certainly not reject it at that point. When we reject whether it's a good fit is when we're not sure because the data is so far off. Okay, so let's go and graph this now, or at least do the calculations. We're going to go into our distributions, and we see down here we have the chi-square, these two. Number 6, the PDF, gives you the point on the curve. We don't want that. The CDF gives us the cumulative area. So we have 7. We're going to go from 2 up to infinity. And we have 5 degrees of freedom. So the notation is lower limit, upper limit, degrees of freedom, similar to with the student t. And we have 0.8491. 0.8491. That's our p-value. So our p-value is 0.8491. So just like before, we're going to make the decision, do not reject the null hypothesis. The reason how we make that decision is we say that the p-value is greater than alpha. Do not reject the null hypothesis. And we conclude that indeed the die does follow the uniform distribution. Well, we're going to do one more. I have a loaded die, and I'm going to do this again with that one. I'm going to start out, and I'm going to have my observed here and my expected. And I rolled the die another 30 times. And again, I expected 5s. But this time I used my loaded die. And when I did this, I had 9. Well, I should put down the 1, 2, 3, 4, 5, 6. I had 9 ones. I had 12 2s when I did this. I had 7 3s. I had 0 4s, 0 5s, and 2 6s when I did this time. So this was my other die that I used. And now I want to do the same thing. I want to see, is the die fair? So the null hypothesis is the die is fair. The die does follow a uniform distribution. The alternate will be that the die does not follow the uniform distribution. So now we're going to enter the data into the calculator. I'm going to do this with just the calculator part right here. And we'll go into L1. I'll show you how to do this just with L1. We'll go into L1. And in L1, we're going to first clear out the old stuff. And I'm going to enter now my observed. 9, 12, 7, 0, 0, 2. Now I'm going to enter the expected in L2. And the expected in this case was all 5s. And now we have the data in here. We'll exit from here, and we're going to set up, we're going to write a little program. And the program will go L1 minus L2, observed minus expected squared. Observed minus expected squared divided by expected. So we have observed minus expected, that quantity squared, divided by expected. We're going to store that in L3. Now how we press the store button is right over here. It says STO with an arrow, that means store. Put that in, L3. Now L3 will have all those numbers that we're going to add up. And we're going to add them up in our list. We go over to math. I went into second list and over to math. And number 5 says sum. And I'm going to sum up L3. And this tells me that my test statistic this time is 25.6. So on a graph for this one, I would have my graph still at the 0 and the 5, but now I have to mark off 25.6. 0, 5, 10, 15, 20, 25. I'm way over here. I bet you can figure out that the p-value is going to be pretty close to 0 from doing this. But if we were to figure it out directly, we would find that the p-value, we're going to go from 5. We have 25.6 with 5 degrees of freedom, and we have a p-value of 0.0001. Well, that tells us that we're going to reject the null hypothesis in this case and conclude that the die is not fair. So my die that I told you was a loaded one is in fact not a fair one. It does not roll uniformly. That's it for the goodness of fit test. The next test that we're going to do is the test for independence. And in this case, we're taking a chart. You saw this in Chapter 3 when we dealt with contingency tables. And we're testing to see, are the factors independent or are they not independent? And so here we have a slightly different type of a case, test for independence. We're testing to see the factors are independent versus the factors are not independent. Our test statistic is calculated the same way. We take each observed minus the expected, square that, and divide by the expected. Our degrees of freedom are slightly different in this case. It's the number of rows minus 1 times the number of columns minus 1. So let's look at an example with this one. We're interested in if the hiking preference and gender are independent events. So we're going to do this on a solution sheet that you have, or you will do it on a solution sheet, but I'm going to set this up. Our null hypothesis is that gender and preference are independent events. The alternate, gender, and preference are not independent events. Well, now what we need to do is we need to go back and find out what we expected. This is the frequency. 100 people were surveyed, and 100 people were surveyed, and out of the females, there were 18 females who said, there were 18 people who said, I'm female and I prefer the coast. There were 16 people who said, I'm female and I prefer the lakes. Well, if we add up all the females, there were 45 that were surveyed and 55 that were male. And if we add down, we have 34, 41, and 25 right over here. Now, if you recall from Chapter 3 from probability, if the factors are independent, so if A and B are independent events, then the probability of A and B equals the probability of A times the probability of B. So if A and B are independent events, then the probability of A and B equals the probability of A times the probability in B. And in fact, it goes the other way around too. If the probability of A and B equals the product of the individual probabilities, then they are independent events. So what we need to figure out is how many we expected on this chart to be female and coast, how many we expected to be female and lakes, and so on. And so we're going to try to figure this out. This is our observed. We observed 18. What we expected if they were independent is that x out of the total would be equal to x out of 45 times x out of 34. And then we solve for x, and we'll have that the expected is equal to 15.3. So if they were independent, we would expect this 18 to be a 15.3. And we could do the same for each one of these. Now, once we get the 15.3, we go back into the formula and do the observed, which is 18, minus the expected, 15.3. Find that difference, square it, divide by the expected, and then add them all up. Add up all 6 of them. All right, let's do this on the calculator. I'm not even going to do it by hand. We're going to go in, and we're going to enter this into a matrix. And so we'll enter into the matrix button is right over here, matrix. So we're going to enter this into our matrix. And I'm going to put it in A. I will edit A. And I have old information in here. I have 2 rows for this times 3 columns. And we'll enter 18, 16, 11, 16, 25, 14. All I'm doing is entering the values that were right here. And now we can exit from here, and when we go back into stat and over to tests, we have a chi-square test for independence. We'll arrow down, and you see it's the very bottom one, or near the very bottom, letter C. And so we're going to do this chi-square test for independence. And this asks us, where is our observed? Well, I'm going to put the observed in A, matrix A. Where is the expected? I'm going to put this actually in B. So I'm going to go into second matrix. And I'm going to arrow down and just put the name. Now B is here. And I can either calculate or draw this. I think I'll draw this time. And we'll see that we have a chi-square test. We have very few degrees of freedom. We have our p-value is a large area that's shaded in. Our p-value is 0.48. Our test statistic is 1.4679. And actually, the graph really does go up and down. But because the degrees of freedom are so few, it's hard for us to see. It's actually climbing up along the axis here. If I were to do this again and go over and arrow down, and this time do the calculate, you'll see that we get our test statistic, our p-value, and our degrees of freedom are 2 in this case. Well, now that we know what the p-value is, 0.48, we need to decide, do we reject or do we not reject the null hypothesis? So now we've seen that our p-value is 0.48, and we make the decision, do we reject or not reject the null hypothesis? So in this case, with a p-value of 0.48, we decide, no, we're not going to reject the null hypothesis, and we would make the decision that our factors are indeed independent. Well, that pretty much wraps up what we're doing for this section. In this section, we had 3 different applications of the chi-square distribution. The first was the goodness of fit test. We did an example of that. We're seeing, does the data fit what we expect it to fit? The next is the independence, to see if factors are independent or if there's a relationship between them. And the last case, the test of a single variance, is testing to see, is the data following within a certain spread, or is it more spread out than we want it to be? We have one more section to go, and that section is Chapter 12, and that's on linear regression and bivariate data. And I will be back with the next segment pretty soon. Bye-bye.